Day 238 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again. Another day, another LeetCode problem. This time we're at day 238 and we're still going strong, y'all. Today we have question number 235, lowest common ancestor of a binary search tree. The difficulty level is medium, but don't worry, we're going to keep the solution as simple and easy to understand as possible. So let's get into it, y'all. So the question says, given a binary search tree, find the lowest common ancestor node of two given nodes in the BST, the binary search tree. According to the definition of LCA on Wikipedia, which stands for lowest common ancestor, the lowest common ancestor is defined between two nodes P and Q as the lowest node and T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So let's break that down so we can see what it is that they're talking about by looking at example 1. Example 1, we have the input root equals a binary search tree 62804790003 and 5. P equals 2 and Q equals 8. The output is 6. Explanation: the LCA of nodes 2 and 8 is 6. So we could look at this example right here, or this picture that they gave us, and we have P equals 2, which is right here, and Q equals 8 right here. Just by looking at this picture, we could tell that 6 is the common ancestor. It's the only common ancestor that they have. Thus, the output is 6, right? So that's kind of a simple example where we have both nodes, they're on different sides of the binary search tree, whereas 2 is on the left subtree, 8 is on the right subtree, where we could just look and see where those two nodes split at, right? Which is 6, the root node. It's the first split of the binary search tree. So let's look at example 2, where it might be a little bit more tricky. They might try to throw some trick questions our way, you never know. And in example 2, we have the two nodes that we're looking for are both in the same subtree, which is the left subtree in this scenario. So let's go through it. And the example 2, the root equals a binary search tree 62804790003 and 5. But this time P equals P equals 2 and Q equals 4. As you can see, 2 is right here on the left subtree, the root of the left subtree, and 4 is right here as a child node on the left subtree. So as we can see, the output is 2 because it says in the question where we allow a node to be a descendant of itself. So we're allowing 2 to be a descendant of itself, and it is the lowest common ancestor between 2 and 4, meaning they both have a common ancestor, and that common ancestor in this case is 2. And when they say the lowest node, as you can see, they're not necessarily talking about the value. They're talking about where it is on the binary tree. So as you can see, this 2 is the lowest ancestor, and up here 6 would be the lowest ancestor, even though it's the root. But down here 2 is the lowest ancestor because it's at a lower level, right, than 6. 6 is also a common ancestor, but 2 is lower than 6 in example 2. That's why the output is 2, because we're looking for the lowest common ancestor, not just any common ancestor. And in this case, if this is the top of the binary tree, this is lower than the top, right? This is below the top, so which would be the root. So that's why the answer is 2. So let's look at example 3, where this time we only have 2 nodes. So, and in this case, well, let's go through. The input root equals 2, 1, equals binary tree 2 and 1, P equals Q, P equals 2, Q equals 1. The output is 2 because by looking at this, since 2 comes first, we know that 2 is the root. And if 2 is the root, then it goes from 2 to 1. That means 2 would be the lowest common ancestor because 2 is going from 2 to 1. Even though they don't have a picture to show us, they don't need one because it's only two nodes, and we know that 2 is the root. So that's why the output is 2. So now that we understand the question, y'all, let's get into the fun part, the actual solution, the part that all keeps us going getting up in the morning. But before we get into the solution, y'all, if you need any new Apple AirPods, don't forget to go check out the link in the description. And then after you do that, don't forget to like, comment, and subscribe. Now, let's get into the solution, y'all. So when we're solving this problem, the first thing we want to do is we want to create a base case to see if the current node or the root is nil and return nil, because if there is no node or there is no root, then we know that there's no LCA that exists. So first, we're just going to check to make sure that there is actually a root node or there's a node at all. So in order to do that, we're going to say guard let root equal root, else, open up the brackets, return nil. And once again, that's just going to make sure that there's a binary tree to even work with. Now we want to check to see if the current root is equal to either P or Q, right? And so this means if it is, then this means that the current node is one of the nodes that we're looking for. So in order to do that, all we have to do is say if root is equal sign, 3 equal signs to P, and this equal sign, this 3 equal sign, just check to see if it's the same instance in memory, right? So that will let us know, just in case two nodes have the similar value. This isn't checking to see if it has the same value. This is checking to see if it is the same object in the memory, right? So which would mean it's the same node that we're looking for without using the equatable protocol. So then we're going to say or root, equal signs Q, meaning it's the node that we're looking for because root and Q will share the same object in memory. It's not necessarily the same value, but it would be the same value. But just in case there were two nodes with the same value or something like that, this is making sure that they're the same object in memory. So then we're going to come down here and we are just going to say return root. Boom, just like that. Now we got to use a little recursion to search the left subtree, right? To search for the LCA in the left subtree. So in order to do that, we're just going to declare a variable called L. We're going to set that equal to lowest common ancestor that we're getting from up here. Then we need to pass in the root, P, and Q. So we're just going to open up the parentheses. We're going to say root.left for the root. Then we're going to say P, comma, Q, just like so. Then we're going to do the same thing for the right side. We need to recursively search for the LCA in the right subtree. So in order to do that, we're just going to do the same thing, except this time we're going to say bar R equals lowest common ancestor, open up the parentheses, root.right, comma, P, comma, Q, just like so. Now we need to check to see if both the left or the right subtrees return nil values, because if one subtree is non-nil, that means that the LCA would be on that subtree. Or if one subtree is nil, then that means both P and Q will be on the left subtree, right? Which is similar to example 2, right? If this subtree was nil, then we know that we only need to search the left subtree. So that's what we're about to handle now. So in order to do that, we just need to see if P and Q are found in different subtrees, then we know we need to search both subtrees, right? So that's what we're going to check. We're going to say if L exclamation point equals nil and two and signs, R exclamation point equals nil. Or so that means if L does not equal nil, that's what this exclamation point. So if L does not equal nil and R does not equal nil, what we are going to do is we are just going to return the root, right? Else, though, we need to say else in case one of them is nil. If L exclamation point equal sign nil, right, then that means only the left tree has a non-nil value, which means the LCA is coming from the left subtree. So we could just say return L. Then we just come down here. If That means if L is equal to nil, that means the right subtree would not be equal to nil. So we could just say else return R, just like that. And that should be all she wrote, y'all. So let's run it, make sure it runs. Wasn't that much code at all. Should be all the code, and it's accepted. So let's submit it, make sure it stays accepted, y'all. Let's see, and look at that, y'all. 54 milliseconds beats 15.38% of users with Swift, y'all. Don't worry about the time complexity right now. We're just focused on getting the solution done and understanding how we got to the solution and how we answer the question. I feel like this is a good solution for that. It's real quick and simple and easy to understand, y'all. So read it, learn it, love it. I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.